And in this section, I would like to discuss two important econometric measures, coefficient of determination and correlation coefficient. We've seen them before, so I believe that won't be completely new for you. As before, the coefficient of determination, denoted by R squared, or also known as goodness of fit, is just a summary measure that tells how well the sample regression line fits the data. This is the definition I've given you in the previous lecture. If you don't like it very much, I have also included another definition. It gives the coefficient of determination gives us the proportion or the percentage of the total variation in the dependent variable explained by the explanatory variable's axis. So, in a sense that this is just some percentage measure of the variation in the dependent variable, which is explained by the independent variable's axis. Here is the formula. It is exactly the same as in the previous lecture, not actually 2 lectures before, I think, or 3. So the properties are the same. The R squared must lie between 0 and 1. The closer it is to 1, the better the fit is. The closer R squared to 0, the worse the fit is, in a sense that there is a very weak relationship between the dependent and independent variables. However, there is small issue with this coefficient of determination that you must be aware of. So if you keep on adding the independent variables, so if you keep on adding x's to your regression, this term here, the residual sum of squares will keep on increasing, which means that the term over here, so it decreasing, right? So this term here will be decreasing, which means that the whole term over here will also keep on decreasing, and so we will be subtracting a smaller and smaller number from 1, which means that R squared will be actually getting higher and higher. And this property is summarized right here. So R squared is a non-decreasing function of the number of explanatory variables. As the number of regressors increases, R squared almost invariably increases and never decreases. So in a sense that the mistake that you might make is that, for example, you will have 2 models, one with 2 independent variables and the other model with 5 independent variables. And when you will be comparing their R squared, you will see that R squared is higher in case of the 5 variable model, and here is an explanation why. But if you hadn't known about this explanation, you would have concluded that the second model is better because R squared is better. Therefore, when you keep on adding variables and make sure not to make a mistake of comparing R squared, because R squared will always be higher in case of the model with more variables. So therefore, you should be very careful when you choose a model based on the value of R squared. However, since econometricians were aware of this problem, they came up with something called adjusted coefficient of determination. So this is just an adjustment of the traditional R squared that takes into account the number of explanatory variables. So in simple words, this measurement here will punish you for adding more extra variables. So actually, instead of increasing due to the increase in the number of explanatory variables, this measure will actually decrease. So in a sense, it punishes us for adding extra variables. So here is the formula as the first one. So if you compare this formula to the previous one, now we've got some extra term in the denominator like n minus k, the difference between sample size, number of observations, and number of parameters, and in the denominator we've got also n minus 1. So this is where this punishment comes from, in a sense. And finally, the partial correlation coefficient. Unfortunately, it's not that easy when it comes to multiple regression analysis. The coefficients become a bit more complicated. So if we would like to know the partial correlation coefficient between y and x2, we need to use this formula. So we need to calculate the individual coefficient between y and x2. R13, this will be between y and x3. R23, that will be the individual correlation coefficient between x2 and x3. And this is the way we calculate the partial correlation between y and x, holding x3 constant. Similar idea for the partial correlation coefficient between y and x3. So in this case, we hold x2 constant, and this is the formula. So we need some individual coefficients, like the correlation coefficient between y and x3, y and x2, x2 and x3, and so on and so forth. And if we would like to get the partial correlation coefficient between x2 and x3, holding y constant, this is what we need to do. So we need the individual coefficient between x2 and x3, y and x2, y and x3, and so on and so forth. So those are the formulas for the partial correlation coefficients in case of multiple regression analysis.